Hey guys, we're going to talk about fluid properties, specifically mass, density, temperature, pressure, so forth. Let's first start talking about extensive versus intensive properties. So extensive properties are those that change when the sample size changes. So imagine I have, let's say, 1 foot cubed of corn syrup, and I doubled that sample size to 2 foot cubes. I doubled the volume. I would double the mass and double maybe some characteristic length. That only makes sense. However, an intensive property, when I double the volume, double the sample size, those properties don't change. So for example, if I double 1 foot cubed of corn syrup, I don't necessarily change the pressure or the density or the temperature of that corn syrup. So we like to work in intensive properties because it simplifies the analysis. So often all of the thermodynamic variables are written in terms of intensive properties. So density, which is mass over volume, is an extensive over an extensive property, which results in an intensive property. And it has units of like slugs per foot cubed or kilograms per pound mass, that sort of thing. Grams per cc over pound mass per foot cubed, which I don't necessarily like this one. I love the slug. All right. Specific volume, you know, is 1 over the density, so it only makes sense that its units would just be the inverse of density. Now density, like any thermodynamic property, can be related to 2 other thermodynamic properties. So here I'm showing density as a function of temperature and pressure, or temperature and internal energy, or pressure and entropy, or whatnot. So any 2 thermodynamic variables can be combined in some equation of state to derive a third thermodynamic variable. And the classic example of this is the ideal gas. So PV equals mRT. I can rearrange this for the specific volume, and you can see that specific volume is then related to temperature over pressure, the ratio of temperature to pressure. So it's also true that most fluids, although this ideal gas is only good for ideal gases, it's true that most fluids are stronger functions of temperature than pressure. All right, let's talk about absolute temperature. So you're familiar with absolute temperature. It's in terms of Rankine or Kelvin, and it can also be related to the relative temperature scales, Fahrenheit and Celsius. You know that these guys are relative to the freezing point of water at standard pressure, and these two are relative to the motion of the molecules. So at absolute temperature, the motion of the molecules comes to rest. Temperature is really an indication of what the molecular motion is. So as I cool the substance, the molecular motion slows, and at absolute 0 temperature, the motion stops. You also know that changes in temperature are equal to each other across scales. So a 10-degree change in Celsius is the same as a 10-degree change in Kelvin. A 10-degree change in Fahrenheit is the same as a 10-degree change in Rankine. Of course, a 10-degree change in Celsius is not the same thing as a 10-degree change in Fahrenheit, but you get the idea. Let's talk about pressure. What is pressure fundamentally? Fundamentally, pressure in a liquid or a gas is the collision of molecules. So we just mentioned this, these molecules are moving, they have temperature, and when they collide against a surface, like the top surface of this vessel, they exert a force on that top surface. So billions and billions of molecules colliding with the top surface, integrated over that surface, gives you a resultant force. Force over area is a pressure. So here's the definition of it. Force over areas of pressure. Keep in mind that it's a thermodynamic variable, so it can be related to any other thermodynamic variables. In this case, temperature and pressure. That's specifically useful for ideal gas relations. It's a strong function of the compression state of fluid, which only makes sense. And pressure itself is a scalar variable, so that's a good point not to forget. We've also made the assumption that we're in the continuum. So we're not thinking about molecular impacts here, that we've got billions and billions of these, so on average we get a pressure. That's part of the continuum assumption. So you might want to review some of the classic pressures, like absolute versus relative pressure. We'll do that in a second. Static, stagnation, dynamic, hydrostatic, thermodynamic versus mechanical pressure. Some of those we'll go over in the course of these lectures, but it's good for you to recall that that pressure has a lot of variability. Now, the absolute versus relative pressure is very similar to the absolute versus relative temperature, but students often confuse these. So the absolute pressure, if I were to ask you what's the pressure in this room right now, it's about 14.7 psi or 101/300 pascals. And that's pretty much considered maybe standard atmospheric pressure. And I've indicated that we're in absolute units with this little subscript or with this A here. And so that means we're above absolute zero, right? And in terms of pressure, absolute zero pressure would be no molecules in the box at all. Like in that previous slide, you saw the molecules impacting the top of the box. To get no pressure means you got to evacuate the box. Now, the relative pressure is relative not to zero molecules in the box, but to atmospheric pressure. So 0 psig would be to say that we're at absolute pressure. We're at atmospheric pressure. 0 pascals gauge means the same thing. So in fact, all of these measures are telling us the same thing. If I were to increase the pressure by 10 psi, then the absolute pressure would be 14.7 psia, and the relative pressure would be 10 psig. If I decrease the pressure by 10 psi, then the absolute pressure would be 4.7, and the relative pressure would be minus 10 psig. Now, nobody likes this minus sign. It's kind of awkward because we're talking about collisions of molecules against the surface. How can you pull on the surface? How can I create negative pressure? You can't, right? So it's just an artifact of the way that we selected what this relative pressure is relative to. So what we do is we change the sign and we call it vacuum. So vacuum pressure and gauge pressures are both part of the relative pressure scale. So it's awkward because I could change the sign of this 10 psig, and this would be minus 10 psi vacuum would actually be above atmospheric pressure. So it's confusing, but it's not that bad. If I were to lower the pressure all the way to 0 psia, no molecules in the box, then the relative pressures would be minus 14 psig and 14.7 psi vacuum. It's worth noting that just like temperature, changes in temperature are the same in Celsius and Kelvin, changes in pressure are also the same in terms of their absolute and relative scale. So if I say the pressure went up by 10 psi, you don't know if I'm talking about 10 psi atmospheric or 10 psi relative. It's the same measure, 10 psi absolute or 10 psi relative. All right, let's go over the last two here. Specific weight is just the quantity rho times g. It appears so often we give it its own variable, gamma. What is that? That's density times gravity, so it's really mass times acceleration, so we get a force over volume, and that force is really the weight over the volume of the fluid. So the specific weight of water is 62.43 pounds per foot cubed, and then you might not remember, but if I say pounds, by default that's pounds force, just like if I say psi, by default that's absolute. The density of water is 1.937 slugs per foot cube. And I like the slug because it is the true measure of density in the BG system, not pounds mass. So if I wanted to calculate the specific weight of water, it would be the density times the gravity, so that's 1.937 times the gravity, and then I need to cancel out the units because I got a whole mess of units. So I use this unit conversion that a pound force is equal to a slug foot per second squared, and the unit conversion then you can see that all of these units cancel beautifully, and you're left with what? Pounds force per foot cubed, and so you end up with 62.32 pound force per foot cubed. Now, if I were to do this in using pounds mass, this is a density, pounds mass, times gravity, and the unit conversion for pounds mass is 32.174 pounds mass is equal to, or times gravity is equal to 1 pound force. So a pound mass is not a pound force. You can see the units then cancel. There we go, and I get pound force over foot cubed. All right, The last one I want to talk about is specific gravity. That's a density over a relative density or a reference density. That's the specific gravity. This should be SG actually. SG, sorry about that. And the reference density for a gas is air at 4 degrees Celsius. So that's either 2.52 times 10 to the minus 3 slugs per foot cubed or 1.205 kilograms per meter cubed. And the reference density for a solid or a liquid is that of water at 4 degrees C. And there's the values there. So what's the density of red oak that has a specific gravity of 0.67? Easy enough. I know that it's a solid, or I'm assuming that it's a solid, and I just take the density. I can just rearrange this to solve for this rho here. So specific gravity in this case times the density of water, and I get the answer of 670 grams per meter cubed. Notice that just like all these FE questions, they're giving you things like this is 0.67 times 1.2. They're giving you kind of common mistakes.